Ralph Stanziola has made the comment on several occasions that we're very fortunate to be working in the field of color because it's so sensitive. When variables are not controlled or when variables are permitted to be changed, we're fortunate to be able to identify color change. A color change doesn't mean that you necessarily have a problem in the manufacture of the color, but it means that someone somewhere along the line has failed to control all of the variables that exist in the process.
Often when a company starts using color instrumentation for the first time, they find that they're able to quantify for the first time the variables that occur in their operation. Often these variables come from kind of mundane situations, things like mixing time or sample preparation. And what we're going to do is look at these items which affect the reproducibility and the repeatability of the product. And we're going to study them from specific industries, but they could relate to almost any industry. All industrial operations that are interested in high-quality color control have to be concerned about the elements of their operation that affect the reproducibility and repeatability of their product. They have to learn something about these factors. When we talk about repeatability, we're talking about the ability to make the same thing over and over again, but it's different from reproducibility. For example, if we had a stock solution of a dye and we made 10 dyings from that stock solution, how close the dyings would compare would be an indication of the repeatability of your dyeing operation. On the other hand, if you made 10 different stock solutions on 10 different days and you made one dyeing from each of those 10 stock solutions, then that would be an indication of the reproducibility of your operation. In terms of color measurement, if you measured one sample 10 times on a spectrophotometer and looked at the variation in the measurements, that is an indication of the repeatability of your spectrophotometer. On the other hand, if you measured one sample on 10 different spectrophotometers, that's an indication of the reproducibility of the spectrophotometers.
Once repeatability and reproducibility have been achieved, a computerized color matching system can be an effective tool in day-to-day applications. For systems to be useful in formulation and correction, however, they require consistent information. This information is gathered through physical samples which describe the unique behavior of each colorant used in the product. The information is then stored in the system. Once this data has been collected, the system expects the materials and process to behave in a consistent way. If they do not, the results provided by the system will not be accurate until the information about the materials and process is updated. However, the system can be used as a tool to identify where inconsistencies in the process are occurring. The performance of a computerized color matching system is dependent on the degree of repeatability and reproducibility of both the materials and the process. This digital output from a color matching system represents the measurements of 2 textile samples. Both samples were made by the same process using the same materials. Each sample should, therefore, closely match the other, but it does not. What could account for the differences between the 2 batches?
Errors in weighing can be one of those mundane factors that causes problems in your plant. You can get a computer output to 6 decimals, but that's not really the problem. The problem is, do you end up in a batch with the amounts of colorant that you think you're putting in the batch? Even though you may have very precise scales, you don't necessarily end up with what you think you have. For example, if in your drug room, in your dyeing operation, you don't keep the lids on your dyes and the dyes pick up water, for every pound of material that you weigh out, you have some dye and some water, and you never really know how much. And since water doesn't dye the fabric, you have an error in the colored effect. If we look at this particular tan problem, you'll note that if we make a 10% weighing error in each of the elements used to make up the tan, that is the red, yellow, and blue, you can see that in this particular example that the red has a much greater influence than either the yellow or blue in its visual impact. If you make an error in the red, the visual impact is greater than either the yellow or the blue. But what's really important, if you look at making a weighing error in the fabric that you're dyeing, it's almost as significant as any other element in the mixture. And yet, textile mills rarely take as much care in weighing their fabric as they do in the dyes that are used in the formula.
To minimize weighing errors, scales and balances need to be accurate. Calibration should be checked on a regular basis. Much like weighing errors, dispensing errors also contribute to color difference.
The paint company was interested in learning the variability of the dispensers in the stores that sold their paint. 24 stores were asked to dispense two formulas, a gold formula and a tan formula, into the same white base. These samples were then compared to the formulas dispensed by the central laboratory. There was a significant variation among the samples. In the particular gold sample that we have in front of us, there was as much as 25 units between the formula dispensed from one store compared to the central laboratory. Well, how come they weren't all the same? They used the same white base, they used the same colorants, and they used the same dispenser. Well, they weren't the same because all of the things that you have to do to get the same volume dispensed each time from the dispenser were not done by each of the stores. The nozzles weren't cleaned every morning. The pastes weren't stirred as often as they should have stirred them. So in fact, when they were assumed they were dispensing a certain volume, they were not.
The importance of accuracy in dispensing is also important when working with dyes. Certain classes of dyes require the use of what are known as stock solutions. A stock solution is generally required when the amount of dye needed for a particular application is too small to be weighed out accurately. Instead, a larger amount of dye is measured using an accurate balance. The dye is then mixed with a precise amount of distilled water. It's important that the proper pipettes and volumetric flasks be used. The resulting stock solution is then dispensed through a metering device, such as a pipette, to create all of the other concentrations of the dye. Any errors made in the preparation of the stock solution will affect the accuracy of all dye concentrations made from it.
Another of the so-called mundane items which affect the reproducibility and repeatability of your product involves mixing time, simple mixing time. I'm not talking about dispersion time. I'm talking about just how long it takes for colorants to be mixed uniformly in a batch. For example, if you take out a sample before the color is mixed uniformly, you're trying to hit a moving target. So you don't really know the condition of your batch. So it's important that you learn how long it takes before the colorants are uniformly mixed in your batch. Color instrumentation can be very helpful in allowing you to quantify for each of the kinds of mixing equipment and containers that you use just how long it does take before you get a representative sample.
This graph shows how mixing time relates to total color difference for paint in a 10-gallon and a 500-gallon tank. The standard represents the material mixed for 60 minutes. In this example, it takes at least 20 minutes of mixing in either tank before a color difference of 1 unit or less is reached. This example illustrates that the delta E of samples taken from either tank before they are thoroughly mixed will not be representative of the batch's true color. The graph shows that it will be necessary to mix both batches for more than 20 minutes in order to achieve a delta E of 1 unit or less. Proper mixing time for any batch can be determined by taking samples at regular intervals and using color instrumentation to identify when the color has stabilized. In the lab as well as in the plant, The mixing process is critical to the quality of samples and the accuracy of data. Make a record of the mixing time and the speed of agitation. Also note the order in which ingredients are added as the sample is mixed. This is especially critical in paint applications in order to minimize flocculation. Flocculation occurs when the pigment particles normally dispersed throughout the paint bond together. This generally results in a batch which appears lighter in color. When a sample exhibiting flocculation is rubbed up, a darker color can be seen. This is because the flocculated pigment is being broken up by the rubbing action. However, when a sample with properly dispersed pigments is rubbed up, the color appears the same throughout and shows no signs of flocculation. The data from this sample represents the true optical properties of these colorants. Another problem that relates to the way pigment is dispersed throughout a sample can best be described by way of an illustration. This ink sample contains blue pigment particles. Normally, the pigment particles are completely encapsulated in the resin. These particles selectively absorb and scatter the various wavelengths of light. The light that does not strike the pigment particles is transmitted to the substrate where it is scattered. An observer sees a mixture of the blue light reflected by the blue pigment and the white light reflected by the substrate. In addition, a small amount of specular reflection, or gloss, may also be seen as light strikes the surface. The chromaticity of this specular reflection is normally the same as the chromaticity of the light source. A white light source will result in a specular reflection that is also white. In some samples, however, the pigment particles are not completely surrounded by resin, but are instead in direct contact with other pigment particles. As the particles become crowded and the space between them becomes smaller, a condition known as overpigmentation occurs. While overpigmentation most commonly occurs in ink samples, it can also occur in paint and plastic samples. In some cases, pigment particles may protrude from the surface as well. A phenomenon sometimes occurs when light strikes this overpigmented sample. Although the chromaticity of the light source may be white, as the light strikes the particles protruding from the surface, the specular reflection appears to take on a cast of a different color. This light combines with the light reflected by the surface and the pigment particles of the sample to create an effect called bronzing. A blue sample that exhibits bronzing will generally appear to have a red cast. The color of this cast will vary depending on the color of the sample. It's important to recognize that while bronzing may accompany an overpigmented sample, not all overpigmented samples will show signs of bronzing. Because it is a surface refractive effect, an ink sample may exhibit bronzing even if it is not overpigmented. Computerized color matching systems often have difficulty when trying to match an overpigmented or bronzed sample. Systems can, however, be of help in determining whether a sample is exhibiting these problems. This is the spectral curve for 25% Rubine red. Its wavelength of maximum absorption is 550 nanometers. This second curve represents another sample that contains a higher concentration of pigment. While the wavelength of maximum absorption has not changed, the curve now begins to flatten in the area of 440 nanometers. A third curve represents a still higher concentration of pigment. Here, the wavelength of maximum absorption has shifted slightly toward the yellow, and the curve flattens even more dramatically in the area of 440 nanometers. Spectral curves can be useful in determining if a sample is overpigmented, whether or not bronzing can be seen. For instrumental evaluation, it is often useful to apply a clear coat over samples which exhibit bronzing. This provides a seal over the pigment particles protruding from the surface. Another approach is to add clear vehicle to the ink before it's printed. Sampling techniques differ from industry to industry. With textiles made by a continuous dyeing process, samples taken from the sides of a large roll of fabric may show a significant color difference when compared to a sample taken from the center of the roll. This is sometimes due to inconsistencies in roller pressure, which may be the result of misadjustment or roller wear. The degree of this side-center-side variation can be quantified through the use of a spectrophotometer, and adjustments in roller pressure can be made. Whether in the plant or in the lab, before an accurate measurement can be taken of a sample, its color should be stabilized. This means that the sample must first be completely dried or cured. In certain materials, such as textiles, paper, and trade sales paints, the moisture content of the sample affects its color. Drying is a process by which moisture is removed from the sample. Karen Gaskins of Interface Flooring Systems comments on fabrics and the effects of drying.
When a fabric comes off of the dryer, as it sits for 5, 10, and 15 minutes, you will see a gradual change in color, and that change in color is due to moisture regain. So therefore, if you're doing, especially if you're doing instrumental measurements, you need to be consistent in the amount of time that it sits after it comes out of the dryer before you take the measurement, because of that gradual change in color due to moisture regain.
Some industries, like the paint industry, the way a test sample is dried can influence the color of the product. For example, it's often necessary to force dry a sample because of time considerations. But very often that sample that's force dried may look quite different than a sample that's allowed to air dry. So you have to learn about the variabilities caused by different methods of drying.
When samples must be force dried because of time constraints, an oven that provides proper circulation should be used. These two samples were made from the same batch of paint. One was air dried and the other was force dried. There appears to be a noticeable color difference between the two samples, which here can only be attributed to the differences in drying methods. A spectrophotometer can be used to measure samples that have been dried differently and determine if the drying method has an effect on the color of the sample. While some samples are dried, others, such as coatings, are cured. Curing is a chemical reaction. Ovens are often used in the curing process. The curing temperature, however, can affect the color of the sample. The oven needs to be checked and calibrated to ensure that the temperature set is constant and uniform throughout. Whether a sample is to be cured or dried, the temperature set must be just high enough to dry or cure the sample completely and evenly. Robert Swain comments on the effect of heat on color in plastic and explains the concept of heat history.
Heat history in the plastics business is generally referred to as the residence time the plastic spends in the melt stage. The product moves from the back end of a machine to the front end of the machine, moving from a solid pellet phase into a molten state. And the amount of time the product is retained in the barrel under this heat is referred to as heat history. Heat history affects the color in several ways. It can cause pigments to discolor if they lack the heat stability to take the heat history. Also, the polymer itself can discolor when subjected to high heat. And the discoloration generally manifests itself in a very wide and noticeable shift in color. It's always helpful to have a little knowledge of what the customer will be doing with your product as you start your color match. With the knowledge of his general operation, you can establish a set of molding conditions that essentially will reproduce what he is experiencing on his production floor. And you can do as a result, you end up doing a color match that anticipates the heat history and the polymer discoloration that his part will, or his plastic will see.
I once worked at a paint company that was very proud of the fact that they would agitate their tint paste several times a day. And since they were making a lot of off-whites, they had just 5 gallons of tint paste out on the floor next to each tank. And several times a day, the man would go over with a paddle and, starting with the yellow paste, would stir it several times. Using the same paddle, he went down to each of the tint paste and obviously was contaminating each one with a little bit of the paste from the previous container. They couldn't believe that that little bit of paste was enough to cause significant variations, but in fact it was. So you have to be reasonable. You have to be able to be sure that if you're going to add a particular blue, it in fact is that blue, not contaminated with some yellow from a different container. You also have to be careful in your operation to make sure that if you're going to use a container that was used before, that you can clean it out properly, because it doesn't take much of a yellow to contaminate a blue, or it doesn't take much to contaminate of a black to contaminate a bright red.
In textile applications, one source of contamination in the laboratory is the use of spatulas for weighing dyes. As a technician is weighing dyes, they take a spatula, and if they don't rinse it between the red and the blue bottle, we will see contamination. Also, in textile applications, many times we're weighing very small amounts of dyes to 3 decimal places. And rather than weighing these small amounts of dyes, we use a dye solution. If the pipettes are not rinsed properly between solutions, we will also see contamination there. Another source of contamination in the pipetting is the method that is used. There are 2 methods: a blowout method where all of the dye liquor is blown out of the pipette versus a graduated method. And this allows you to get 2 different amounts of dye into the dye formula. So those areas need to be addressed also. Even though these certain contaminations may not be seen by the eye, the human eye, if you're measuring on a spectrophotometer, these contaminations come out and jump out immediately at you.
Contamination is often a major factor affecting the repeatability and reproducibility of colored samples made in both the plant and the lab. A spectrophotometer can help identify contaminated samples. Each colorant has a unique spectral curve. This is the curve for a blue dye commonly used to dye wool. This second curve represents another batch of the same colorant. However, this curve appears slightly different from the first, specifically around the area of 420 to 460 nanometers. This difference may be an indication of contamination. Since the spectral curves are different, the 2 batches of this colorant are not the same. To minimize the chance of contamination, all equipment should be thoroughly cleaned before mixing a new sample or applying a new colorant. These 2 samples show how cleaning procedures can affect the color of a plastic. Both samples are supposed to be the same color. The sample on the left was made directly after the equipment was used to make a sample of a different color. The sample on the right was made after a batch of clear resin had been run through the equipment to purge it of residue from the other color.